My watch says it's time to start. So we're going to do a review today on Chapter 16, Acids and Bases for Chem 100. And that's in preparation for the exam on this topic due next Tuesday, which would be the 9th, November 9th. Okay, so this is the review document that you can find in Blackboard. There's a key that goes with it. In fact, this is the key. And there's also a handwritten work problems as usual. All right, and I've picked out some of these that I'm going to go through one at a time till we got them all done. We'll start with, let's see, number 3. Okay, so there's number 3. You see the whole thing. You know, before we get started on this, I think probably a short review might be helpful. Right, what's an acid? An acid always starts with at least one hydrogen. Right. Sometimes they have 2, sometimes they have 3. I've never seen one with 4, but it's possible. So you have an acid with a hydrogen, and then you have the rest of the molecule that we just designate A for acid. So when you put this molecule in solution, aqueous solution, we can write it 2 ways. We can write it as the accurate representation of what reaction occurs. We'll do that one first. So when we put it in water, that acid reacts with water. And the proton is transferred to the water molecule. So you get left over, you get that, and you get the hydronium ion. Okay? Now this is typical for all acids, and this is the convention. Transfer 1 proton at a time, or 1 hydrogen ion, same thing. That makes this the acid. I see Katie. Okay. I just got started.
Did you get my email about why I missed Tuesday?
I don't remember seeing it. Were you sick?
Yeah, I had a stomach flu all morning and couldn't make it to class. So
Okay, I understand. And the video should be, actually the video is posted now.
yeah,
Correct.
I tried to watch it yesterday, but I had a math exam for Algebra 109, so I couldn't watch much of it yesterday. So
Okay. So you just got some catching up to do is all. And this will be recorded, so if a lot of it doesn't make sense, then that's okay. I mean, once you look at the lecture and then come back and look at this, it should fall into place. And I got a leaky marker here again. Let's see if I can clean it up. You just get what you pay for. These are probably the cheapest ones I can find. Which makes sense because they don't last very long. Okay, let's leave that out in case I need it again. Okay, I was just starting off. The first one I had picked out on the review document is number 3. But I thought it better, rather than just jump right into that problem, do a little bit of review on what actually occurs when an acid is placed in aqueous solution. This is my generic acid. Right? It always has a hydrogen to start with, and then the rest of the molecule. When we put it in an aqueous solution, it reacts with water, transfers that proton to the water molecule, and that produces this special compound, the hydronium ion. And it leaves behind the negative, the anion of this part of the molecule. And when we represent an acid going into solution, it's always one proton lost at a time. Right? So one proton here transferred. If we had an acid with two protons available, like this, then we would have the other proton will stay behind. But this species here can also undergo dissolution. Right? So it's a sequential reaction. Like that, and it produces another hydronium. Okay, so that's characteristic. When we talk about acids and bases, this is acid because, according to Bronsted and Lowry definition, it donates a proton. That's an acid. The receiver of the proton is the base. So in this case, water is the base. It accepts the proton. And on this side, we have the conjugate base. And this is the conjugate acid. This is the conjugate base of that acid. And this is the conjugate acid of that base. All that means is this reaction can go backwards and forwards. It can return. So this could become a base because it would now accept a proton from any source. But in this scenario, it accepts the proton back from that species. This one donates the proton, so now it's an acid. Okay, so with that in mind, the other characteristic of acids and bases, well, acids, let's stick with acids for now. We can express this also in an abbreviated form, and it's often written that way. So if we take this one as is, we can say that species loses a proton and produces this anion. So you'll often see an acid dissociation written this way, when this is actually what happens in solution. But the equilibrium equation, the expression, and you'll have to look at the lecture video to get a little more information on equilibrium. When we write the equilibrium constant for this, and we put a little a there for acid, that expression is the equilibrium concentration of the hydrogen ions times the equilibrium concentration of the conjugate base divided by the equilibrium concentration of the acid. That's what the square brackets mean. The concentration of that species once equilibrium is reached. And in short, equilibrium just means that the rate that this is produced in that direction is equal to the rate that it returns. Okay. So once we know this value can tell us just how strong that acid is, right? Because if it produces lots of these protons, then it's a stronger acid. If it produces just a few, then it's a weaker acid. And that means that if it dissociates a lot, then it's on this side. A lot of this and very little of that. Which makes this value here, since that's big and that's small, it makes Ka very large. But if it doesn't dissociate easily, and most of it is like this, and very little of it is like that, then this term becomes small, and this term becomes large, and the Ka is small. So the smaller the Ka, the weaker the acid. Then the other concept that we need before we can answer number 3 is that if you have a strong acid, it produces lots of these. And it wants to be over here. If that's the case, then what about the conjugate base? If this is the acid, and this is the conjugate base, what about the strength of the conjugate base? Does it want protons? If that's a strong acid, then it's all the way over here, and this is a weak base. So strong acids produce weak bases, weak conjugate bases. And weak acids produce strong conjugate bases. Because the equilibrium wants to be over here, that means this conjugate base is looking for protons. And if it can find them, it'll take them and produce this species. Okay, so weak acids produce strong conjugate bases, strong acids produce weak conjugate bases. Okay, so now I think we can answer number 3. I think we can answer it. Let's see. Which of the following is the strongest conjugate acid? Conjugate acid? Strongest conjugate acid. That's kind of funny because these are acids already. Right? So how would they produce a conjugate acid? Maybe that's a typographical error. Let me look at my worked problem and see if I can make sense of that. Here it is. Number 3. All right. I think that's poorly worded. In fact, we should probably not say conjugate acid because these are all acids, right? They're proton donors. That one has a proton to donate. This one, this one. That ammonium ion could lose one of its protons, right? So these are all acids to begin with. Which one is the strongest of all these acids? Let's put it that way. Do we have enough information, really, to know? We could probably, reason it out. And I think that's the approach that I took in the worked problems. But to be absolutely certain of which one of these is the strongest acid, you need that Ka value. That tells you what the equilibrium is going to be in aqueous solution. So let's approach it that way. How about, let's see, A, B, C, D, and E all the same? That's unlikely. So we have HOCl, HCN, HF, and NH4 plus. All right. So what is this going to do when it dissociates? It makes a hydrogen ion plus that anion. That's one of those when we went through acid naming conventions. This is the hypochlorite ion, which means this would be hypochlorous acid. This one that's the cyanide polyatomic ion. So this is no oxygen in the molecule, so it's hydrocyanic acid. This one is hydrofluoric acid. And this one's the ammonium polyatomic ion. So if it loses a proton, what does it produce? Does that. Okay, so in order to judge the strength of these acids, we need to know the K value. What's the Ka for each one? All right, so I've got it here. And let's see. Here we go. This one is 6.2 times 10 to the minus 10. This one is 3.5 times 10 to the minus 8. This one is, ammonium is 5.6 times 10 to the minus 10. And fluoride, the HF, is 6.3 times 10 to the minus 4. Okay? So that tells us something about their equilibrium. The larger the K value, the stronger the acid. So first I would look at the powers of 10. Right? That's smaller than that one. That one's smaller than that one. This is smaller than, this is bigger than either one of those, so it's in the middle. But this one, right here, means that HF, hydrofluoric acid, is the strongest acid of this bunch. So that's definitive. These values don't lie. That means the answer here, HF, is true. But if you're not given that information, it's a little more difficult to determine. You have to reason it out. And I think this is a better way to approach it, if you're given that information. So they're not all the same, obviously. Okay, while we're here, if this one is the strongest acid, that means this one, as a conjugate base, is the weakest base. In other words, it has the least attraction for protons of each of these. Okay, because it's the strongest acid, that's the weakest base. So let's flip it around. Which one would be the strongest base? It would be the conjugate base of the weakest acid. So the weakest acid would be the smallest value of K. Right? And it looks like there's 10 to the minus 10, but this coefficient 5.6 is less than 6.2. So this is the weakest acid, NH4 plus. That makes NH3 the strongest conjugate base of this group. Okay? All right. That was 3, sort of. I added some information to that one so that we could solve it easily. Let's move on down to number 4. Let's see, I'm going to have to scroll that one, otherwise it'll chop the top off of it. Here we go. So number 4. Calculate hydrogen ion concentration. That's what that means. You want to know this value. What's the concentration of hydrogen ions? And we're talking molarity, moles per liter, in a solution that has a pH of 8.82. So the pH is 8.82. What's the hydrogen ion concentration? Well, in the lecture, I described the mathematical derivation of pH. And it's really simple. I mean, it's just pure math. The only chemistry involved is what's that concentration of hydrogen ions. The pH, by definition, is minus the common log, base 10, of the hydrogen ion concentration at equilibrium. Okay, so all you need to know is this value, take the log of it, in your calculator and then change the sign. And you have pH. So this problem is working in reverse. So in order to understand how to solve this problem, you need to know how logarithms work. Right? So this log is actually, since it's base 10, this value, well, we need to move the negative sign over here because you can't do reverse operations here with a negative sign. So we have to say this, minus pH equals the log of hydrogen ion concentrations, like that. So now, by definition, this log function is 10 to the minus pH equals hydrogen ion concentrations. Or in generic form, if you say the log of x equals y, that means that y is the power of 10. That equals x. Okay? Sometimes we call this the anti-log. So the anti-log of this, the anti-log of this would be our hydrogen ion concentration. But most calculators don't have an anti-log key. They have a powers of 10 key. So that's what you want to focus on. If you have a key that says log on your calculator, then above it as a function, what do they call it? You get the function key. And above it, they'll have 10 to the x, like that. So that's the one you use for solving this, but you got to remember to move that negative sign over here. So if we want to evaluate this pH in terms of hydrogen ion concentration, then we just need to put pH here, 8.82. Okay, that means this will be negative 8.82. Now we can do 10 to the negative 8.82. That will give you the hydrogen ion concentration. And it should be, let's see, 1.5 times 10 to the minus 9th mole. Okay? This is purely a mathematical operation. And it was done by Sorensen in order to simplify the expression of hydrogen ion concentrations, the acidity of a solution. It was a simplification process. Rather than talk about hydrogen ion concentration in his reaction mixtures, he wanted a simpler version, and he created this pH in order to do that. Okay, that was 4. Let's see. And is there any value to doing 5? Okay, yeah, let's do 5. A solution is prepared by dissolving 111.9 grams of HCl gas, 111.9 grams of hydrogen chloride gas. We're going to dissolve that in 160 liters of solution. So 160.0, yes, liters of solution. And the question is, what's the pH? pH is the question. Okay, this is a multi-step problem. And if you work backwards, what do you need to know to calculate the pH? You need to know the hydrogen ion concentrations, right? pH equals negative log of hydrogen ion concentration. Okay, so how do we figure that? Well, you need to know the concentration of the acid. And in this case, you also need to recognize that this, in aqueous solution, is a strong acid. And in chemical terms, a strong acid is one that completely dissociates. If you know the concentration of HCl in solution, then you automatically know the hydrogen ion concentration because it goes like this, no return, and produces that. So if you know the concentration here, you know that one because there's none of this left. It all goes into solution. So we need to find out what's the concentration here. Well, we know the grams, right? And we know the final solution. So remember molarity, the definition of molarity equals moles per unit volume. And this has to be in liters, right? So we need the moles of HCl, right? We know how to do that. 111.9 grams of HCl. We need a conversion factor that cancels grams and leaves us with moles. And right, whenever you see grams and moles as a quotient, think molar mass. So HCl would be what? Let's see, 35.45 for chlorine and 1.01 for hydrogen. So that's 36.46 grams per mole. We just put that right down here, 36.46 grams per mole. And that calculation will give us the number of moles of HCl. Let's see, 111.9, 36.46 divided. Oops, I went the wrong direction. Try that again. 36.46. There we go. So that is 3.069 moles. Now we can find, this is moles of HCl. And that, by definition of a strong acid, that is also 3.069 moles of hydrogen ions. So now we can find out this concentration of hydrogen ions. So the moles, 3.069 moles of hydrogen ions divided by the final solution, right? The volume has to be solution, not solid for molarity. So that's 160.0 liters. I get 1.9, let's see, 4 significant figures. 1.918 times 10 to the minus 2 molar. Okay, now that we know the molarity of the hydrogen ions, we can find the pH. We just need to plug it into this formula. pH equals negative log of 1.918 times 10 to the minus 2 molar. So I've already got it in my calculator. I'll just take the log of it and change the sign. Now, there was also something said in the lecture about significant figures. Logarithms are funny. When you have 4 significant figures in this part of the calculation, the logarithm can have that many decimal points. So the pH can have 4 decimal points because there are 4 significant figures. So if I do that, I find that I have 1.7171 4 decimal points. That's my pH. And let's see. Okay, this was rounded off. So In this case, pick the best answer. If you pick none of these, then technically you would be right. But you'd have to argue your case. And since the exam is in Blackboard, then you'd have to call me up. You'd have to email me and say, it counted me wrong. It should be this value. It should be none of these. In which case, I would give you the correct, give you the credit for it. Otherwise, pick the best answer, which in this case, I think is probably 1.72. Okay, so that's how we would calculate the pH for this solution. Like I said, it's multi-step. You work it backwards. You say, what do we have now? What do we need? Right? Can we get what we need out of that information? And it turns out, by definition, yes, we can. We got all the information we need to determine the pH of that solution. And that is a very low pH, which means it's very acid. Right? When we discussed in lecture the pH scale, because it's logarithmic and it introduces the negative sign in order to eliminate, we don't want a negative value here, so we change the sign. As it turns out, smaller numbers of pH means stronger acid solution, and larger numbers of pH means weaker acid solutions, or even basic. A basic solution would be one that, let's see, pH greater than 7 is basic. pH less than 7 is acidic. Right? So what is it at exactly 7? That's neutral. In fact, pH 7 is the pH of distilled, deionized water. It's pure water is pH 7. That's our central point, neutral. Now, that doesn't mean it doesn't have hydrogen ions in that solution. It does. It just doesn't have many of them. Plus, all the hydrogen ions in pure water produce at the same rate, the same concentration, hydroxyls. So let me show you that. Okay, so this is what pure water does. And I'm going to use the abbreviated form, right? Instead of reacting water with itself, I'm going to say this water produces hydrogen ions and hydroxyl ions. Okay? It does that. Just pure water, liquid, produces these ions. And it does so only in very, very small amounts. So notice that when this one, for every one of these, it produces one of those and one of those. So whatever this concentration is, same concentration for hydroxyls. And in pure water, the Ka for that solution is 1 times 10 to the minus 14. Right? Remember our expression, Ka is equal to the product concentrations, the product of the product concentrations at equilibrium divided by the concentration of the reactants. But the rule is, if it's a pure liquid or a solid, it doesn't enter into the calculation, because during this reaction, the concentration of water doesn't change. So it has no impact on the K. So we leave it out. So in this case, the Ka is derived from hydrogen ions and hydroxyl ions only. And that's equal to 1 times 10 to the minus 14. Okay? So what do each one of these have to be in order to satisfy that constant? This is constant. It doesn't change. As long as the temperature stays the same, that's constant. So this would have to be 10 to the minus 7, and this would have to be 10 to the minus 7. to equal that value. Okay, that's pure water. So if we take the pH of this value, what's the log of 10 to the minus 7? Well, it's base 10, so the log of that is minus 7. And then we change the sign, we just put a negative in front of it. So that means the pH of this solution equals 7. All right? But we can also do that same arithmetic, the logarithm, for OH. So if we take the negative log of OH minus, we get a POH. And that also is 7 at neutrality, pure water. Okay? And whenever you got any other type of reaction going on in water, this is still happening. I mean, this doesn't shut down just because we put a strong acid in there. Now, it may be insignificant compared to the strong acid. That's true. But if you put a weak acid in there, then there's competition. Which one of these produces more hydrogen ions, the water or the weak acid? Right. Then you have to think about that, and that's a little beyond this course. Okay, so I'm trying to give you background at the same time we're working these problems, since you missed the lecture. And I don't want you to be completely lost in what I'm saying here. All right, that was 5. How about 6? I'm pretty sure that was a choice. Yeah, number 6. A solution has a hydroxyl ion concentration of this. The pH of this solution is what? Okay. Well, let's see. What are we given? The hydroxyl ion concentration is equal to 5 times 10 to the minus 4 molar. And the question is, what's the pH? Well, I just mentioned that you can do a POH calculation, just the way you do a pH. But you can also do a pK for, if this is the K value for, and then actually we give it a different subscript. For water, it's special, a KW. That's equal to our 1 times 10 to the minus 14. Okay, and that is calculated from hydrogen ion concentrations and hydroxyl concentrations. Right. So we can calculate the hydroxyl concentration. Well, actually, it's given. Right. And if we stick that in there, it's like any equation. If we put that in there, we know that this is our only unknown. We can solve for that. So if we put 5 times 10 to the minus 4 here, then we can solve for this by saying, divide that into this. So the hydrogen ion concentrations will be, I should be able to do this in my head. 1 divided by 5 is 0.20. And then 10 to the minus 4 divided into 10 to the minus 14 is 10 to the minus 10. And that's equal to 2 times 10 to the minus 11. Okay, so we know the hydrogen ion concentration. Now we can calculate the pH. We just need the negative log of 2 times 10 to the minus 11. I can't do that one in my head. So I'll use my calculator to, there we go. Take the log of it, change the sign. So I get, see, 2 significant figures, so I can have 2 decimal places. 1, 0, point 70 pH. There it is, right here. Okay, that's one way to solve the problem. There's another way that I discussed in the lecture that actually is, I think, easier. but you need some background to do it. So 10.7 is the answer. Let's see if we can get it the other way. So here we have, this is true. Right here, this expression for equilibrium is true. What if we take the negative log of that entire equation? So the negative log of Kw would be pKw, right? It's just math, it's logarithms. And that's equal to pH and then pOH. But what do you do when you take the log? This is an identity of logarithms. The log of x times y is the same as the log of x plus the log of y. Okay? Go back to your math book and you'll see that. So when we do that, that means this pH is plus pOH. So what's the pKw? What's the negative log of this value? Well, that's 1. That makes it easy. 10 to the 4 minus 14 will be minus 14, change the sign. So this value is 14 pKw. And this is whatever it is, right? pH plus pOH. So if we calculate the pOH of this value, and I'll need my calculator for that one. Let's see, 5 exponent 4 there, and take the log of that, change the sign. I get 3.30. So the pOH is equal to 3.30. Right? So if we know this is 3.30, all we need to do is subtract that from 14. And I get 10, actually. pH equals 10.70. There it is. So that's another way of doing it. And I think this is easier. Okay, that was 6. Let's see. If I keep it up, I'm going to run out of time. So let's see. I might have to skip 1 or 2 of them to get where we're going. Okay, let's go to 7. Come on. No, not behaving. There we go. This is a thought problem. We know that as water is heated, the hydrogen ion concentration increases. So if we have water here and it produces hydrogen ions and hydroxyl ions, and at equilibrium at 25 degrees, 25 degrees Celsius, this concentration is going to be 1 times 10 to the minus 7 molar. And this one is going to be the same. Okay? If we heat it, that means we're driving the reaction this way. We're breaking this apart and making more hydrogen ions. Okay? At the same time, though, since this is the only reactant, when it breaks apart, it makes more hydrogen ions, but it also makes the same number of hydroxyl ions, right? Because they come from the same place. So with that in mind, let's look at the question. This means what? Water is still neutral? Well, yeah. As long as the hydrogen ions and the hydroxyl ions are equal in concentration, we have a neutral solution. So that's true. Hydrogen ions greater than hydroxyls? No. We just said that they're equal no matter what the temperature, because they come from the same source. This one is also false. Hydroxyl also increases. That's true. And it increases to the same concentration as the hydrogen ions. So A and D are both true. Okay. I thought that was important enough to stop and look at. Let's see, 7. Do we want to do 8? Okay. Yeah, we can do 8. I need to scroll it a little bit though. Okay. 8. So based upon this equation, HSO3 minus Cn minus produces HCN and SO3 2 minus. Okay, what's happening here? It looks to me like this proton is being donated and this cyanide ion is accepting it to produce that acid and this anion. Okay, so what does that mean in terms of acid-base reaction? That means this is the acid according to Bronsted and Lowry. This is the base because it accepts the proton. So that means this is the conjugate base. And this is the conjugate acid. Okay. Now, with our abbreviation of acids and bases, this would be an A, this would be a B, this would be a B, and this would be an A. So ABAB should be our answer. ABAB. Acid base, acid base. Okay? That was number 8. Let's see, do we want to tackle number 9? Okay, number 9 goes to the definition of what a Bronsted-Lowry acid is. So in order to have a conjugate acid-base pair, what they mean by that is you have the acid, and then next to it you have the conjugate base. Right, so what does that look like? You need something with one proton. It can be an ion too, as long as it has the one proton to donate. That's your acid. And then the conjugate base is what's left over after that acid is gone. Okay, that's what we're after, conjugate acid-base pair. So you need 2 things. You need to have this part of the molecule the same on both sides. The A has to be the same. Plus, the conjugate base can only be missing one proton. If it's missing more than one proton, then it's not the conjugate base, because we only do one proton at a time. Okay, let's see which one matches. Let's see. There are no squirrely answers in here, so we can work our way down. When we find the right answer, that's it. So HPO4 2 minus, HPO4 2 minus, and then it says PO4 3 minus is the conjugate base. Is that true? Well, is this valid? Does it do that? Yeah. There's the A part right here and here. This one changed from a 2 minus to a 3 minus because it left those electrons behind when it became this proton. And 3 minus and a plus is 2 minus, so the charge is balanced. That's true. That's our answer. If we look at any of these others, we'd see something like Actually, this one's picked up a proton. That one can't be it. It's going the wrong direction, right? That makes this a base, and that's a conjugate acid. How about this one? Well, if it loses a proton, it can't be a plus charge. It has to be a minus charge. So that one can't be it. If this one loses a proton and produces HF minus, technically that could work, except that this compound doesn't exist, right? And this one lost 2 protons to get there. This one lost 1, yeah, it gives it that. But that's chemically, it doesn't exist. You can't make that compound. Simply because fluoride ion is -1. When you add a proton to it, you get a neutral compound. If this were HF and that were F minus, okay, I'll go for that. But the best answer here is this one. So here's a case, best answer is A. Let's see, we want to look at 10 is another case of identifying the acid-base pair. Number 11 is another case of back calculating the anti-log of the negative pH to find the hydrogen ion concentrations. We already had one of those. So we're not going to stop on number 11. Let's see if, go down to 15, see if that's something new. What's the pH of an acid solution containing 0.044 molar HNO3? This one is straightforward also. We've done one just like it, only it was more complicated. You have to recognize that nitric acid is strong. Nitric acid in aqueous solution will produce all of this and all of that. Right? So there's your hydrogen ion concentration, which will be equal to the concentration of nitric acid in solution because it's a strong acid. So this is the concentration of hydrogen ions also. And you just do the calculation and you got your answer. So we're not going to stop on that. How about, let's see, 16. What's the pH of a 4.9 molar solution of HClO4? Okay, the point of this one, perchloric acid, HClO4, is a strong acid. So we know the concentration is 4.9 molar and produces 4.9 molar hydrogen ion concentration. If you do the conversion to pH, you will get a negative number. That's a valid logarithmic conversion based on our convention, negative log of the hydrogen ion concentration. It's a negative number. We don't use negative pHs very often. When you get to this high concentration, we just stick with the concentration. But the conversion, the calculation is valid. You can calculate a negative pH, and that's what this answer represents. Right? It's not a trick. It is a true calculation. Let's see. What's the pH of this solution? Right? Nitric acid is a strong acid. Just do the conversion. Right? And you should get 0.6. Let's see. 18. Yeah, 18. The solution has a pH of 3.16. The pOH of this solution. All right. Here's where you can use that pKw conversion that I showed you earlier. Right? So we'll do this one. 18. If you know that the pH is 3.16, then the pOH is 14 minus 3.16. So the answer is 10.84. Now we know, is this solution acidic or basic? Well, based on the pH, it's definitely acidic. It's less than 7. But if you look at the pOH and you're given pOH, if the pOH is greater than 7, it's acidic. All right. So let's see if we can get into something a little different, I hope. How about 20? Actually works on the concept. We've already introduced the concept. Works on the concept of definition of a buffer. So now that we know how to measure pH in a solution, either based upon the hydrogen ion concentration and a calculation to do the pH, or we have instruments that will measure pH. We have electronic meters that use a special probe, and you put it in your solution, and based upon some chemistry that happens at the tip of that probe, it's interpreted by the instrument as a pH value, and it gives you that value on the meter. But back to a buffered solution. A buffered solution, by definition, is a solution that is a mixture, usually, of a weak acid and its conjugate base. So if you put these two in the right combination, then if you add an acid, any acid to that solution, the pH will only change very slightly. In other words, the buffer resists a change in pH. Whether you add an acid or a base, doesn't matter. So based upon that definition, let's see what we got here. Which of these is true about a buffered solution? The solution will not change its pH very much, even if a strong base is added. That's true. The solution resists any change in hydrogen ion concentrations. That's true. It doesn't fix the hydrogen ion concentration at a constant value. It only resists the change. If you put pure water and you add hydrochloric or hydrogen chloride to it, then it will dissociate and produce a drastic change in hydrogen ion concentrations and lower the pH quite a bit with just a little bit of hydrochloric acid. But if it's buffered, when you add that same amount of acid, the pH will nudge just ever so slightly. Any hydrogen ions added will react with the conjugate base of the weak acid already in solution. Okay, if we have a weak acid here, okay, and let's do the complete reaction. It's going to react with water and produce that plus that. Okay, so here's the weak acid, and here's the conjugate base. So if and these are in solution together, right? They're all in the mix. So if you add hydrogen ions here, what's it going to react with? Well, if this is a weak acid, that makes this a strong base. And what we mean by a strong base is it is very attracted to protons, either free protons, or it may even strip protons off some other species. Like it would be very good at taking protons away from water. If that's a strong base, then it could react with water to produce the weak acid plus hydroxyls. Okay? It's a strong base, which means it's a good acceptor of protons. All right, so back to this discussion. When we add hydrogen ions, what's it going to react with? It's not going to react over here with water again. Well, it could. But the dominant reaction is with that strong base. So when we add hydrogen ions, these two combine to produce the weak acid. So what have we done? We've consumed most, but not all, of the hydrogen ions. Okay? So that means we added hydrogen ions, but they do not influence the pH very much. So that's true also. Those hydrogen ions react with the conjugate base of this weak acid. The solution will not change its pH very much, even if a concentrated acid is added. That's just another way of saying C. So all of these are true. Each one of those statements. In the lecture, I also say something about what would happen if we add a base, if we add hydroxyls to the solution. What does it react with? Well, remember, hydroxyls are based upon this reaction. This is a very, very weak acid. Its K value is 10 to the minus 14. That means it wants to be over here. It's a weak acid. That makes hydroxyl an extremely strong base. It will take protons like that. So what does it do? It reacts with this one, takes a proton from that hydronium, makes a water molecule, and leaves behind another water molecule, right? You take a proton from that, you get H2O. You add a proton to this, you get H2O. So that reaction produces that. That's what happens to the hydroxyls when you add them to this buffered solution. All right, that was 20. I know I'm going to run out of time, so I'll just keep going. Let's see, 20. How about 24? Here we go. A solution has hydroxyl concentration 3 times 10 to the minus 7. The hydrogen ion concentration in this solution is what? In this case, it's probably more efficient to use the K expression. 24. All right, Kw equals 1 times 10 to the minus 14, which is equal to the hydrogen ion concentration plus the hydroxyl ion concentration. And if we know the hydroxyl is 3 times 10 to the minus 7, then we have an equation in one unknown. We just divide this by that, and that gives us the hydrogen ion concentration of 3 times 10 to the minus 8. Okay? All right, 24, 27. Let's see if it's different. Okay. A weak acid, HOCl, hypochlorous acid, is in solution with dissolved sodium hypochlorite. Okay, what do they have in common? They have that that hypochlorite anion is common to both of them. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? This is another buffer problem. So the reaction we're interested in is this one. Now I'm going to use the abbreviated form this time. There we go. This is the hypochlorous acid, the weak acid. This is added to the solution as the salt of the hypochlorite ion. In other words, this goes into solution like that and produces that ion. The sodium ion is a spectator, so it doesn't enter into the reaction at all. So we add this to the solution along with that, and that's how we get the balance between the two. Okay? So now we have some of this and some of that in solution. All right, now we're going to add, let's see, what are we going to add? Acid. So we add extra protons. What does it react with? That's the weak acid. That's the strong conjugate base. So these two get together and produce that. So the species that it reacts with is this one right here, the hypochlorite ion. Okay, that was 27, 28. Which statement is true for a strong base solution with a concentration greater than 1 molar? All right, so let's approach this one logically. A strong base with a concentration of 1 molar. So whatever our base happens to be, it's got the hydroxyls in it. Whatever that happens to be, this concentration is the same concentration as the hydroxyls. So that means this one here is equal to 1 molar. Well, actually, it says greater than. So if it's greater than 1 molar, what does that say about the relationship here? Well, let's see. Is this going to be a basic solution or an acidic solution? It's going to be basic, very basic. Basic solution. So that means that the pH cannot be less than 0. That would be acidic. Let's see. How about pH less than 14? Let's see, what would the pH be? Well, it would have to be greater than negative log of 1. Well, that's hydroxyl concentration, excuse me. Let's say negative log of 1 is equal to 1. Right? 10 to what power equals 1? 0. So this is equal to the pOH. And the if it were greater than 1, say it's 2. Let's say 10. 10 would be easier to do. So the negative log of 10 is 10 to what power? That's equal to 1 equals pOH. So it's greater than 0, could be 1. It's going bigger and bigger pOH. So what does that say about the pH? Well, in this case, the pH is equal to 14. In this case, the pH is 13. Is that right? 10 to what power? Oh, that's negative 1, excuse me. Negative 1. Right? I forgot my sign. The sign didn't come in here because 0 is 0. Negative 1 is pOH. So pH would be 15. Okay? So why did I do that? Well, I wanted to be able to answer this question. C, is pH less than 14? Well, if it's greater than 0, or less than 0 for pOH, then pH would have to be greater than 14. Right? So that one can't be true. So now we're left with, are 2 of these true? Maybe. Let's see. pH is greater than pOH. Is that true? pH is always greater than pOH. That's true. So pOH can't be greater than pH. Right? It keeps getting negative, more negative. So the answer here has to be A. pH is greater than pOH. That was kind of tricky. 28, let's see, about 30. The solution with a pH of 2 is how many times more acidic? More acidic should be than a solution with a pH of 6. 30. pH of 2. We got one solution that has a pH of 2 compared to a pH of 6. Okay. How many times more acidic? What we're saying is, what's the concentration of hydrogen ions for this one compared to that one? Remember, this is a logarithmic scale. So it goes up by, when you change the pH 1 unit, you change the hydrogen ion or the hydroxyl ion concentrations by a factor of 10. So for each pH, it's 10 times the actual concentration. So we compare these, right? 2 to 4. How many times did it go? Well, 3 to 4 to 5 to 6. So that's 1, 2, 3, 4. 4, 10 to the 4th power is actually what we're saying, which is equal to 10,000. 10,000 times more concentrated pH 2 here. All right. That's 30. How about, let's see, 32. A buffered solution contains HNO2. Buffered solution contains 32. If a buffered solution contains HNO2, what reaction is going on here? It's going like this, producing hydrogen ions plus NO2 minus. Okay, how do we get that NO2 minus in solution? We can't rely on this to produce it because it's a weak acid. It won't produce enough, right? So we need to add extra NO2. So how do we get it in there? Well, you put it in there in a way that does not include hydrogen ions, which means you need a soluble salt of NO2. Potassium or sodium are good choices. So you add some of this with some of that, and now you get the balance between this one and this one. You have to have enough of that one in solution in order to absorb the added protons. Okay, so which one of these satisfies? Well, let's see, NO2, NO2, NO2. This is the only one that gives you NO2. So that is the answer. You have to add extra NO2 as the salt. Now, in this course, we don't discuss the significance of those concentrations, right? We do that in general chemistry. But if it ever comes up, the best buffer is to have equal concentrations of the weak acid and the conjugate base. Equal concentrations, that's a perfect buffer solution. I just don't have time to explain why it is right now. That was 32. How about 33? Do we get anything new from 33? Consider this reaction. Acetic acid and water makes the hydronium ion and acetate ion. Which species is the conjugate acid? Well, the conjugate acid has to be derived from the base. So in this reaction, that's the acid, and this is the base. So the conjugate acid of that base is the hydronium ion right here. Okay? Definition. 35. Which of the following is not a conjugate acid-base pair? All right, so in this case, we're saying all of them are conjugate acid-base pairs except for one. So let's see. 2 protons here, none there. That can't happen. Not for our definition to be valid. It has to lose 1 proton only. So this one is false, and we found our answer. The rest of them, you have this A species here on both sides, plus 1 proton is lost. This loses 1 proton. This one loses 1 proton. This one loses 1 proton. Okay. So A is wrong. How about, let's see. I was going to do 37, but we already discussed 37 earlier on. And I incorporated information on this one in the, I think, number 3. Which one is the strongest conjugate base? This one, you need to understand that if you're going to find the strongest conjugate base, you need to find the weakest acid from which each one of these is derived. So you add a proton to that one, proton to that one, proton to that one, proton to that one. And then you find the K value for the dissociation of that acid. The weakest one will produce the strongest base. And as it turns out, those numbers that I put on the board earlier for number 3, if you look at those numbers, we find that NH4 plus produces NH3 plus a proton. And that is the weakest acid. NH4 plus is the weakest acid of all that group. So that it makes the strongest conjugate base. This is its base, conjugate base. So that's why the answer is C in this case. Now, if you're not given that information, if you're not given those K values, then it's difficult to determine, right? Because we remember that HCN, hydrocyanic acid, and NH4 plus have very, very similar K values. The only difference between them is in the coefficients. NH4 plus has a slightly lower coefficient, which makes it a weaker acid. Right? So the coin toss would be between HCN and NH4 plus. And without that information, you can't tell exactly which one is which. All right, let's see. Did I skip one that I wanted to do? Yeah, let me go back. 38. What's the OH concentration in a solution that has a pH of 3.76? All right, we did one, and we've done several like this. If you know the OH, if you know the pH is 3.76, then you can calculate the hydrogen ion concentration. Actually, it'd be simpler to do this. 14 minus that value. Right? Yeah. This would be the POH. And then you do your conversion here to the OH concentration. So OH minus concentration would be 10 to the minus 10.24. And that should be equal to 5.8 times 10 to the minus 11. Okay, let's see, that was 38. 39. 39 is a similar exercise. You just convert backwards, do the anti-log of the negative pH. So we're not going to stop on that one. Let's see, 39. 40 is 40 new. Solid calcium hydroxide dissolved in water until the pH of the solution is 10.39. The hydroxide ion concentration of the solution. All right. Same thing. Subtract this from 14, gives you the POH. Then you do the anti-log conversion back to the OH concentration. Get your answer. So we're not going to spend time on that one. That's a simple conversion. How about, let's see, is 41 valid? Do we need to look at it? Choose the pair of concentrations that cannot be in a given aqueous solution at 25. Okay. So remember this. No matter what else is happening in the solution, this one is always there. Kw equals 1 times 10 to the minus 14. And that's equal to the hydrogen ion concentration times the hydroxyl ion concentration. That's always there. So whatever these happen to be, when you multiply them, they have to equal that number. That's what we're getting at here. So if this one is 10 to the minus 13, what does this one have to be? 10 to the minus 1. Right? Has to be. So that one is false. If we look at the next one, let's see, 10 molar. So what's that? 10 to the first power. That means this has to be 10 to the minus 15 in order to be 10 to the minus 14. So that was true. This one, minus 3 and minus 11 is minus 14. Minus 7 and minus 7 is minus 14. Those are all true. A is the only false one in there. And it's based on that definition. And that reaction that always occurs in aqueous solution. Okay, 41. Let's see, is 42 valuable? What is the pH of a solution prepared by dissolving 96.1 grams of sodium hydroxide in enough water to make 3.2 liters? All we have to do here is convert this to moles. That's a strong base. It produces hydrogen ion concentrations. Maybe we ought to do it. It is multi-step. (42) All right, we're given 96.1 grams of sodium hydroxide and a final volume of 3.2 liters. So in order to calculate the pH, we need to know what's the hydrogen ion concentration. Or we could at the very least find out what the hydroxyl ion concentration is. We can do that first. We just need the moles of this. Right? We just need to multiply it by whatever its molar mass is, divide it by its molar mass. So sodium is 23, I think. Yeah. Sodium is 23. Oxygen is 16. Hydrogen is 1.01. Let's see. That's 9, 10 is 40. 40.01. So we divide 40.01 into that value. We get 2.402. Hydroxyls. Okay, that's because this is a strong base. So if we know the concentration of Sodium hydroxide, we know the concentration of hydroxide. Now, what's the negative log of that value? Let's see, log, change sign. That would be, let me do that again. Okay, just want to confirm. Is that right? Yeah, okay. It's a negative 0.306. 3 decimal places, 0.306 is pOH. So the pH is equal to 14 minus a minus 0.306. So I get 14.38 and 381. Oops, what did I do wrong? Did something wrong. Is this right? It looks reasonable, so that one's right. The negative log of this would be 2.402. Change the sign. Oh, that's where I made my mistake. I misread this value. So this is 0.386. Okay, that's a negative number. Then 14 minus pOH is pH. So a minus. That's 386. So 14, well, that's still not right. Oh, boy, am I having trouble today. That's not the concentration. This is the concentration. Whew. 3.2 liters. That's 0.7506 molar. Now the pOH is equal to the negative log of that value, which is 0.1246. And the pH is equal to 14 minus that value. $13.88. There we go. All right, that was 42. And let's see, coming down the wire. And maybe 8 minutes left. Let's see, selectively. Oh, that's it. There are no more problems. Let's see. Well, a solution with a pH of 2.17. It's less than 7, so it has to be acidic. Okay, The pH of solution at 25, in which hydroxyls equal that. So you can do it either way. POH subtracted from 14 and you should get 9.54. You know it's going to be basic. Why? Because the concentration is greater than 10 to the minus 7. If it's greater than 10 to the minus 7, it has to be basic. And then we confirm it by the pH here is greater than 7. Okay, that's it.